So welcome everyone, and especially Niccolo, thank you so much for joining us today to give us this talk. I'm very happy to introduce Niccolo Bucciantini from the Observatory Astrofisica di Arcetri in Italy. The title of today's talk is IXPE Studies of Pulsars and Their Nebulae. Brief introduction, Niccolo got his PhD, his degree in physics at the University of Florence, and a PhD at the Arcetri Observatory. He then moved to UC Berkeley, where he was first a research scholar and then a Hubble Fellow, and later to Nordita in Sweden. Since 2011, he has been a staff member at the Arcetri Observatory and also an adjunct professor at the physics department at the University of Florence. His main expertise is on high-energy astrophysical sources, relativistic fluid dynamics, non-thermal emission processes, numerical methods, with a particular focus on modeling of pulsars and pulsar wind nebulae. And he has been a member of the IXPE core team of IXPE, which, as you know, has been producing really spectacular results. So let's welcome Niccolo and get started. As I mentioned earlier, the format of the talk is 50 minutes typically with questions, and then that is followed by a general discussion. And please mute yourself if you're not speaking. And if you're not directly getting our mailings, please just send me an email and I will add you to our mailing list. All right. Thank you, Niccolo. And please get started.
Thank you all. And let me share. I hope all of you can see. So I'm pleased to talk to you and to present the results that we got in the first 2.5 years of observation with IXPE. And these talks is the result of the work of many people in the collaboration. So I'm talking also on behalf of them. Now, you will excuse me for a brief introduction on PWN. This just serves to set the stage. You might be quite familiar with this issue, but just you to remember what we are looking at. Essentially, we are looking at a system that's formed out of a combination of a rapidly rotating neutron stars, which is our pulsar, that produces an outflow, essentially through pair creation in the magnetosphere, and that inflates the nebula. So in reality, these systems give us information both on the condition in the nebula itself, but the nebula can be used, and we have been trying to use it as an imager for the pulsar. So there's a very complex physics, it's a multi-scale physics that tied the small-scale dynamics of the pulsar magnetosphere all the way to the evolution of the supernova remnant. We do care about these objects because they are a relevant object for high-energy astrophysics for essentially two reasons. They are beautiful labs where you can investigate in detail astrophysical processes. They are galactic, they're well resolved, and they are well constrained, unlike many other extragalactic systems. So to a certain point, they are the benchmark against which we have tested our understanding, for example, of particle accelerations or emission processes. Now, if you look at the Crab Nebula, you will immediately see that this is probably the most efficient particle accelerator, non-thermal particle accelerator that we know. This is the spectrum of the Crab. It is the synchrotron component of the spectrum of the Crab that extends all the way from the ionospheric cutoff at about 30 megahertz down to 150 MeV at the synchrotron limit. Now, this is a completely non-thermal spectrum, apart from an infrared bump due to the dust, but essentially can be easily described as a set of broken power law with a set of break that can either be attributed to intrinsic acceleration changes or synchrotron cooling. The point is that there isn't a Maxwellian, even if you try look to find it. So this is telling you that particles that the pulsar inject into the nebula somehow are accelerated with an incredibly high efficiency to a non-thermal distribution. Now, this is also seen if you look at this object in different ways. But now, I'm making this point because, of course, PWN have been looked at in polarization for a long time. They are essentially very bright radio sources, and radio gives you polarization almost for free with the radio telescope. So we do have plenty of information on the radio property, except that if you look at radio in these systems, you will get a very different picture than when you look at high energy. In particular, this is due to the fact that radio particles are low energy particles that typically have a cooling time which is longer than the age of the system, and as such, they more or less trace the entire evolutionary history. They are volume filling, as we used to say. X-ray particles, on the other hand, are particles that are freshly injected. In the crab, X-ray emitting particles have a lifetime of about 20 years. So they trace the instantaneous injection condition of the system itself. And they are, for this reason, an imager of how the pulsar wind gets slowed down in the shock, gets accelerated, and flows in the vicinity of the shock itself. So they probe the acceleration region to a certain extent. This is also quite well seen if you look at the crab at different wavelengths, because you will immediately see that there is a shrinkage of the nebula as you go to higher energy, which is taken to be a clear indication that high energy particles at least are injected by the pulsar and are accelerated at the termination and not throughout the nebula. Now, until now, as you might have noticed, I have only cited one object, which is the Crab nebula. This is a problem in our understanding of PWN, because the Crab nebula is a beautiful object. It has been observed since Bevis' time by virtually every single instrument that stares at the sky. We know almost everything of this object. We even know the day he was born. But the problem is, just because of that, we tend to have an idea of a PWN which is strongly skewed toward what's happening in the crab. So we have a good idea of what's going on in the crab, thinking that that is what is going on also in other PWN, or that the crab is somehow a copycat of other systems, might not be the correct way of approaching this entire class of objects. There is a large diversity, and polarization measures have revealed some of this important diversity in ways were not obvious from the beginning. Now, we know these systems are highly polarized, as I told you. We have a polarization in radio, and typically this high level of polarization that was measured in radio and in optical has always taken as a signature, as a clear-cut signature of synchrotron emission. These are synchrotron dominated. Unlike supernova remnant, where there are lots of emission lines and you have to deal with a thermal contribution which might be dominating, PWN are a very clean system. So in the IXPE band, 2 to 8 keV, they are basically pure non-thermal synchrotron emission, and you can forget about modeling any thermal contribution. There might be some thermal contribution coming from filaments, but that's totally negligible, and the few systems where it has been tried to figure out, it does not amount to a contribution that can compromise a measure of the intrinsic polarization. So if we look at X-ray, which is what we care about in this system, you will see that all these objects show what is known as jet torus structure. So in X-ray, they have a very clear and defined axisymmetric morphology characterized by the presence of this ring or tori, and that are supposed to trace what is thought to be the equatorial plane of the pulsar. Somehow they are supposed to trace the energy injection along the equatorial plane. Plus, these systems show a clear evidence of a jet. And a jet that seems to originate very close to the pulsar. We do see systems that are jet-dominated. For example, PSR B1509 has a very strong jet. The jet is much stronger than the torus. There are the systems like Bila, where the jet is incredibly weaker, but it's present. Crab is something in between. So this feature is not the same for everything, but it's clearly present in all the objects where we have observations that are deep enough to actually appreciate this. Now, these observations, the presence of a jet in the crab was noticed since the first Chandra observation, and it was immediately evident that it was a problem. And the reason is that you would expect what we see in this picture to actually depend strongly on the injection condition of the wind. So what do we know about the wind of a pulsar? Well, we do have decent model. I would say now we have a very sophisticated models, but in the last 20 years, we have been developing and increasing and improving on the model that we have for a pulsar wind. Order zero, for the kind of systems we are dealing with, we can safely assume that the inner magnetosphere is mostly in a force-free regime. This might not be true for all pulsars. Gamma ray emitting pulsars have a very high gamma ray efficiency, and that casts doubt about the fact that you might have your magnetosphere in a fully force-free regime. There might be charge-starving region. But in general, for the pulsar we are dealing with, like the Crab or other younger systems, probably force-free is a good approximation. Their gamma ray efficiency, their radiation efficiency is not that high to suggest the presence of the break of the force-free assumption. Now, we can compute, and we have a model for the structure of the wind from an oblique rotator, a force-free oblique rotator. And the general expectation is that far away from the light cylinder, once this wind interacts with the surrounding environment, it will mostly be a toroidal wind. So naively, you would expect that the bubble, the PWN, will somehow reflect the injection of these twisted magnetic field. And this is what is actually seen. If you take a few systems like G106, for example, you will see this beautiful polarization structure. This is the magnetic field we are showing here. They clearly trace the presence of a magnetic loop within the system. Now, if you take this image, you will claim that everything is fine and good, and we have a good understanding of this object, and that fits the bill, but there are other things. So in the past, what we have been trying to do is try to connect the properties of the wind to the properties of the nebula. And these have been done essentially by using numerical simulation. So this is an example of a slice through a numerical simulation, a very early one, I would say, that show essentially the interaction of a relativistic wind confined by the parent supernova remnant. So to give you an idea, the region A is occupied by this very fast wind, which, according to what we got from force-free simulation of pulsar magnetosphere, should be stronger on the equatorial plane than in the pole. The fact that the wind has a latitude dependence by itself causes the shock to be oblate, to be at a farther distance along the equator than at the pole. And this has trickled down in a series of consequences. The shock is no more a very, say, perpendicular shock in the sense of the fluid, not of the magnetic field, but it has vorticity downstream. This vorticity creates high velocity channel in the pulsar. This high velocity channel drives turbulence, and depending on the strength of the magnetic field, can even lead to process of recollimation. In particular, it was noted since the beginning that if the magnetization is high enough, you can have recollimating flow within the nebula itself that give rise to the jet. Now, this is a very good important point because force-free simulation of a pulsar magnetosphere, or for all that we know, all simulation of pulsar magnetosphere don't show the formation of any jet. So the jet that we see in PWN, if they come straight from the pulsar, there is something that we don't clearly understand of how pulsar magnetosphere work. The general idea was put forward at the beginning by Yuri Lyubatsky was that you could form the jet by recollimating the outflow in the nebula. It's a complicated process, but it requires strong magnetic field. And the jet will come out of a toothpaste effect. So in a certain sense, the structure, the velocity structure that you see in the nebula and the magnetic field structure that you have in the nebula is strongly tied to the injection condition. So by changing the wind, you can change the structure of the nebula. And by changing the structure of the nebula, you would expect to change its observational property. So what we have been doing in the past is try to simulate what we observe, so the synchrotron emission of the PWN, by adopting different recipe for how particles are accelerated at the shock. Essentially, the idea is very simple. You decide on your favorite acceleration model at the shock, then you have a simulation, you can transport particles within the simulation, they will lose energy because of synchrotron emission, because of adiabatic losses. You will take into account that you are dealing with a relativistic system, so there is boosting, there is magnetic enhancement, and other stuff, and you would compute your emissivity and integrate along the line of sight, until you get something that looks the way your object looks in the sky. Now, this is quite important because, of course, you don't observe a velocity structure or magnetic field structure, you observe synchrotron emission. On the other hand, your simulation allows you to turn on and off by hand the region you care about and check where the feature that you observe in the maps come from. And this has been very successful in reproducing some of the features of the crab, of giving us an idea of where some of the structure of the crabs are seen. So this is the result. What you can clearly see, this is a simulation on top where you do observe, compare with an HST image of the inner region of the crab. This is an optical image that highlight what are known as the wisps, and very close to the pulsar at the center, you will get also something that is the so-called knot, which is a bright spot observed in optical and which can only be seen by a HST because or telescope with adaptive optics because it's at about 1 arcsecond or less than 1 arcsecond distance from the pulsar, so it's very hard to separate in general. Now we know, because from the simulation, we have a good idea of where all those features come from, and the fact that they trace a different portion of the shock. So this tells you that we are on the good tracks. We can reproduce several of the features that we observe. So we have a vague idea where they come from. We can pinpoint them. The pictures roughly, from a qualitative point of view, holds up. And throughout the year, by adopting different parameters and toying with the numbers, we have been able to get good model of the Crab Nebula. So this is the best that we have been able to achieve in, I would say, 15 years of works. So this is an Chandra image of the crab in X-ray, and this is what we get with a numerical model. Now, I will be honest with you, this is a good model of the underlying observation, but it's not perfect. It does reproduce the object where they are, the features where they are. It gives you the presence of ring, knots, tori, but there is a good qualitative agreement, but when you start doing quantitative analysis, you will start to see some difference and something that doesn't work out, and I will come back later on this system. The overall problem, however, of all these analysis lies in the fact that we don't know how particles are accelerated at this shock system, at the relativistic shock. And attempt to get a robust acceleration mechanisms that will work have essentially failed. Also because the systems show quite a diversity, so something that might work to explain the spectrum of the crab might not work in other systems. There are essentially two main mechanisms that have been put forward to explain the non-thermal spectrum. One is the standard Fermi acceleration at shock, the DSA. The problem with the pulsar wind shock is that they are awful shock to accelerate by pairs. Simply because these are essentially highly superluminal shock. The wind is strongly relativistic. The Lorentz factor expected in a pulsar wind is, in the worst case, 10 to the 3, 10 to the 4, more likely is of order of 10 to the 5. Probably not 10 to the 6 as an earlier estimate, but still very high. The magnetic field is supposed to be almost completely toroidal at large distance, which means that the magnetic field is almost completely orthogonal to the shock normal. And these are terrible conditions to accelerate particles. Simply, particles are attached to magnetic field and they flow downstreams and they never manage to get back to the shock unless the magnetization is so incredibly small that de facto the shock behaves as if it was unmagnetized and particles are not really attached to the magnetic field from this point of view. This, however, is a very tricky business because to reproduce the observation, to give you a jet, to get this nebular recollimation of the flow, you need a very high magnetization in the wind. Much higher, about, I would say, a factor, an order of magnitude, probably a factor 20, 30, at least higher than what you need in order to get efficient Fermi acceleration. So if this mechanism works, it cannot work over the entire shock front. It might work in some localized region, very close to the equator, but ultimately it's not an efficient mechanism to produce the bulk of non-thermal particles that you see. And it will only explain, in any case, the high energy emission. It's never going to be able to explain the radio, which is much flatter than e to the minus 2 or minus 2.3, which is the number that you get once you go into the relativistic regime. An alternative approach is to assume that acceleration doesn't happen through standard shock crossing, but through reconnection. And the idea is quite simple. If you have an oblique rotator, you will have a magnetic field of opposite polarity, the so-called ballerina skirts in the wind. And once this wind hosting magnetic field of opposite polarity just crashes into the surrounding supernova remnant, this current sheet will be compressed. You will have essentially force reconnection. These will drive tearing modes. Tearing modes will drive turbulence, that will drive the formation of unscreened electric field. Particle will be accelerated in this mess. The mechanism is not so straightforward as standard DSA acceleration. It depends on the distance of the stripes, on the number of charge carrier, on the multiplicity of the wind, on the separation of the stripes, on the efficiency of the tearing mode. There is more leverage to have things work. And the result is that it also gives you flatter spectra. So it's a mechanism that might work for radio, essentially. And this is something typical of turbulence. So turbulence has a certain level of freedom, certain degrees of freedom to provide you with a spectra of different slope that shocks, strong shocks typically don't have. And ultimately, it is the bouncing of particle in tearing mode and the fact that you have unscreened electric field that provides part of the acceleration. The problem with this model is that it is very hard to have this model make it compatible with what we would expect from magnetospheric model. Essentially, this model works quite well if you have a very high multiplicity in the wind, lots of pairs, to say you, and if you have a very strong current shift. Fortunately, standard pulsar wind theory tells you that if you have a very high multiplicity, magnetic field is likely to dissipate before it gets to the shock. So, as I said, you have a model that works, but putting all of this together might be quite cumbersome. Now, there is another possibility, as I said, and is that you might have, especially for the radio, it has been suggested, distributed turbulence within this nebula, and this distributed turbulence might provide some form of acceleration. Actually, turbulence helps to explain lots of the phenomenology. There are plenty of phenomenology in these systems that might be helped by the presence of turbulence. So there are essentially various lines of reasoning that suggest the presence of turbulence. One is the fact that in the crab we do observe gamma ray flares. And all the existing models that are needed to explain gamma ray flare rely on the fact that you need to have very highly localized strong magnetic field. You have a reconnection with a milli-Gauss strength magnetic field in a system where at the termination shock it is already very, very hard to get above 200 microgauss. Now, to get on very small scale, very strong current shift, it's a typical manifestation of intermittency. And intermittency is a typical manifestation of turbulence. If you think of a system behaving like in a Gaussian way, the chance of getting the condition necessary to produce your reconnecting layer that will give you a gamma ray flare are virtually non-existent. So you will never see this flaring activity. We do see turbulence in simulation. As I say, this oblique shock creates lots of vorticity, and vorticity is the main driver of turbulence in the bulk of the nebula. There are also other indications that suggest that turbulence is present. In particular, one which has been used in the past before flares and simulation were even present or done, is the fact that if you compare the extent of the system in radio with what we see in X-ray, we find that the X-ray is typically much larger than what one would expect from a naive laminar model of matter flowing in the nebula. Essentially, you would expect the X-ray size of the crab to be much smaller. And a similar argument can be drawn if you look, for example, at the spatial variation of the spectral index of optical on X-ray emission, which is much shallower than what we would expect from a simple laminar transport of the particle together with cooling. So we can go back at the simulation that I was showing you before and just point at this. So this is a comparison of the simulation I was showing with the map of the crab. And now I'll tell you what of this simulation doesn't work out quite easily. The main things that doesn't work out is that simulation does reproduce a torus and an inner ring, but the torus that you see in the simulation is much more peaked on axis than what you see in the data. The torus in the data is much more broader, much more uniform. Essentially, the simulation seems to underpredict the luminosity of the side of the torus. So apparently, this standard simulation that we are performing don't really get the correct emissivity of the systems where we care about. The simulation looks more compatible with the optical and with the X-ray. There are other things of our simulation which works in a qualitative way, but not in a quantitative way. For example, the variability. So this is a movie of an old simulation that shows you maps taken evolution over a few years of evolution of a simulated PWM. And we do see wisps that vary, and that's fine because we do see variability in the wisps and in the torus. Point is that the simulations are way too variable. So you can clearly see here, you get a lot of variability feature that appears to disappear. There is essentially a Q factor or a variability factor of order 100%. None of this is seen in the object. The object vary, but overall the structures are very stable. Yes, the torus of the Crab nebula luminosity change a little bit, but it doesn't change dramatically. We have been observing the Crab nebula for 24 years now, and the torus sits there more or less with the same size and the same luminosity, and the inner ring sits there more or less with the same size and same luminosity. There is some variability, but not that so strong. The other issue that we have is that in simulation, in axisymmetric simulation, typically the average integrated X-ray polarization is very high, as of order of 40–50%. And we know in the Crab, the integrated polarization has been known since the late 70s, is 20%. So definitely the early simulation that we were performing had way too much ordered magnetic field. And they had way too much, let's say, variability in there. Now, one can think that this was a limitation of earlier simulation, which were mostly axisymmetric, but unfortunately, no. We have similar problems even when we go to 3D. So it's true that 3D tend to help in some way, but it doesn't help completely. What 3D shows is that in the inner region, where the X-ray comes from, the structure is not that different from what we get in axisymmetric 2D simulation. And so the same problem that we had before, the variability problem, the excess variability in the emission maps, is still there. On the other hand, 3D simulations have this awful tendency to have X-ray emitting particles that diffuse outward quite easily. And the point is that they tend to give a very low fraction of the polarization. It's very, very hard in 3D simulation to go above 15%. Now, you might think that 15% is not much different than 20%, and we are all astrophysicists and we know how numbers work. But the point is that we are dealing with a number that's bound to be between 0 and 70 at most, probably no more than 50 once you account for integration and geometric factor. So going from 15 to 20 is not that easy. And when I say in simulation is very hard, it means that if I take 20 simulation, I get 15, at most 17. It's really getting to 20% is more than 3 sigma. So the large scale 3D dynamics is not the solution. Now, the problem is that it's very hard already to do 3D simulation. These are incredibly demanding. The system is very old. The time scale involved are quite long. So in my opinion is that we are hitting a typical problem that we have nowadays in our simulation. We can either perform very accurate simulation on processes on small scale, reconnection, acceleration, the development of turbulence, and so on, or we can perform large 3D simulation that try to model the large scale structure of the systems, inflow and outflow, development of instabilities, and things like that. Problem is that between these two, there are orders of magnitude of dynamical range. So it's very, very hard to understand how to embed the small scale simulation into the large scale dynamic, but vice versa, our large scale dynamics lack the information of the small scale that is typically unresolved. So the problem of treating the unresolved scale, the subgrading problems in numerical simulation is probably today is one of the most thought for and most investigated problems in the numerical field. For all that we concern at these times, the question is what is the role of a possible unresolved turbulence that you might have on the small scale characteristic, for example, of the flaring, in terms of the emission map that you have. Likely, there is a way of modeling unresolved turbulence in terms of its observational properties and in terms of its polarization properties. So this is a simple analytic model that tells you essentially that once you know the level of magnetic fluctuation that you have at a local scale, you can compute the local emissivity in terms of Stokes parameter and the local polarization in terms of Stokes parameter. So independently of the formula that you use, what is shown here is, for example, in the systems where you have a delta B, a fluctuating magnetic field component, which is more or less of the same order of the average large scale ordered field, you would expect your systems to be depolarized by about 50%. So polarization or depolarization with respect to theoretical maximum expectation is a direct measure of the amount of energy that you have in the turbulent component. So you can use it to try to figure out if there is turbulence and how turbulence is distributed. Now, to give you an example of how this recipe was applied before IXPE, when we only had emission, this is what happened if you take one of these simplified boosted torus models that have been around the literature since the work of N.G. Romani in 2004, and you add turbulence. And you would immediately see that it does exactly what we hoped it should do. So turbulence makes these ring and tori look like wider, which is exactly the problem that we had with the original models of the graph. So ideally, by adding turbulence, you might resolve some of these issues. You might lower the polarization that from your 50% will go down to 20, and you might make your map looks more like what they really are in reality. And the original estimate, for example, in the case of the crab, was that in order to get the average polarization of the systems and the typical width of the torus, you would expect to have a level of turbulence in these systems, delta B over B of order unity. This is factoring already some geometrical depolarization due to the fact that this is a torus, you are looking at incline, so there are a few things to be taken into account. Now, many of what I've said refer essentially to young systems, to systems where essentially we do observe a PWN which is well confined within the supernova remnant. These are two typical examples. One is G21.5, which is the one on the bottom, sorry, and is also one that was on the list of observed target, and we have just submitted a paper about it. In the case of IXPE, we have also an observation of an older system, the systems where the PWN is already interacting, or we think it's starting to interact with the supernova remnant. So we know that at a later time, the PWN will come into contact with the supernova remnant shell, and at that time, there is a phase known as reverberation, where the dynamics and the evolution of the PWN will be modified by the supernova remnant. There are a few systems we know, or we think, are in this exact condition. One is EC443, but perhaps the most famous is the Vela PWN. Now, you can see this image. This is an X-ray image of Vela. You can see the X-ray PWN. There is the bright spot in the middle, right where it sits the pulsar. And this is the bright core of the PWN. It was that regions with the arc and the jet that I was showing in the first image. So if you look carefully, what we are looking here are freshly injected particles, X-ray. The pulsar is not really centered on the X-ray, but the fact that this is interacting with the supernova remnant is particularly well shown if you look at low energy particles. And you can look at low energy particle by looking at the TeV emission. This is inverse Compton from particles that would be emitting radio. Radio is not very easy to observe in general, and these systems are quite crowded. If you look at TeV, this is what you see. And you can immediately clearly see that the gamma ray PWN is totally displaced with respect to where the pulsar is. There is actually almost no gamma ray emission at the location of the pulsar. The idea is that essentially because of the interaction with the reverse shock, the relic material, the low energy particles that have been accumulating there throughout the age of the system, have been pushed away from where the pulsar is. And the pulsar is reforming continuously a new and fresh PWN, which mostly shine in X-ray, or at least in freshly injected particles. So the PWN that we are looking now reflect indeed conditions that represent very well. It's a clean environment for the pulsar, or it might be it's not a clean environment, it's a very messy environment because of interaction. We don't know this, but at least it does, it's a different environment than what we sample with the younger one. So why do we care why do we care about polarization? So a beautiful example that I typically do to my students is this. Now, this is an image of one of our objects. It's MSH 1552 in X-ray. You see a torus and you see a jet. Now, synchrotron is a beautiful tracer of the properties of the particle, but unfortunately, it's very degenerate with respect to magnetic geometry. So what I'm showing here now are 3 toy models tuned to these objects, where the jet, which is the features we care about in the case of these systems, has been simulated adopting 3 very different geometry of the magnetic field. One is a purely radial magnetic field, if you want, purely poloidal. One is a purely toroidal magnetic field, a bunch of loops in the jet. And another one assumes that the jet is a fully chaotic system, highly turbulent. Now, if you have a good eye, you might guess which one is which by looking at how the luminosity changes along the jet. But remember, these are toy simulations. Reality is much different. In reality, the jet is bent. The jet finds itself embedded in a PWN with its own X-ray halo that might have gradients. So it's not so obvious that variation in luminosity or trend traces exactly the properties of the magnetic field or the properties of whatever it sits around. So if you want to guess what, I will give you a few seconds. You can try to pinpoint which one of these should be a purely toroidal magnetic field or a magnetic field with loop. And some of you might have guessed it, this is the answer. So the point is that polarization will immediately tell you which one is. It will give you immediately an idea of the structure of the magnetic field. And this ultimately will help you to understand what is the configuration and the dynamics of these very same systems. Different magnetic field geometry have different implications in terms of the variability, the possible origin of turbulence, the possible origin of instability, the possible role of reconnection and turbulence into the acceleration. Now, why don't we do this with radio? Well, there are several reasons. First reason is because radio particles trace the bulk of the nebula. So it's true, there are a few systems. This is VILA, this is G106, where the magnetic field does exactly what it's supposed to do. Beautiful loops, everything works, it's toroidal. This is the picture you put in your lectures, the pictures you put in your book to say that you understand everything. Then you look at other systems and it's not this. You have other systems where the magnetic field is fully radial. Now, how do you make a sense of this? Well, you can easily make a sense of this by stating, well, you know what? The magnetic field is radial because I have Rayleigh-Taylor instability. Rayleigh-Taylor instability drives me fingers, and these fingers stretch the magnetic field. But there is a beautiful system where we see Rayleigh-Taylor instability. It's the Crab Nebula. And also in G20, in 3C58, we have some hint of Rayleigh-Taylor instability. So let's look there. And when we look there, we see something that doesn't come out anything, either radial or toroidal. It's very amorphous. It doesn't correlate with anything. Maybe in 3C58, maybe follow the radio loops. So it's polarization in radio, it's really a mess. We have an explanation, as I say, for each object, but we do not have an explanation for every object. So, okay, I will not spend too much time on IXPE. We know that it was launched now 3 years ago, and it has been active since. Observing now about 6 PWN has been observed. I will point to the 3 aspects of the IXPE satellite that I care most. And these are the sensitivity, the MDP, is a measure of effective area. Essentially, X-ray polarization is a very potent stuff, and you need to collect lots of photons. Angular resolution is important. It's important for essentially, otherwise you get integrated measure. It's very difficult to disentangle local polarization variation, the presence of turbulence, the patchiness, and especially for the pulsar, this has been fundamental. Without angular resolution, we would have never been able to measure a polarization signal from the pulsar. And the other is the energy resolution. IXPE was chosen to operate in the Chandra energy range, and that has been a blessing because we can use Chandra as a fiducial data for the intensity. And we can use the Chandra data to deconvolve the polarization map, even at the low resolution of IXPE. So we can benefit from Chandra imaging and Chandra data to get information on scale that technically are not resolved by IXPE, by doing the convolution. Okay, this is how it works. Essentially, it's a photon. There is this gas pixel detector, and it traces the particle track. Now, there are issues in tracing the particle track and identifying them. They have some repercussion on extended source, but I will not discuss much of this. Point is that this has allowed for the first time to do space resolved polarimetry. So I'm going to present the result. This is the results for the crowd. Now, in terms of geometry, as you can see, the magnetic field fits the bill. You have a beautiful toroidal magnetic field. Whether that's what you would expect. There are issues in terms of the degree of polarization, polarized fraction. Polarized fraction does not follow the symmetry, the main symmetry axis of the nebula. It's much more enhanced on the north side and the south side. It's not much an axis. The polarization is also very small, close to the pulsar in the inner region, where you would have expected the magnetic field to be more ordered. So for some reason, it seems that the polarization does not peak at the center, but it seems that it peaks, or the order of the magnetic field peaks at the edge of the torus, or if you want, at the boundary of the Rayleigh-Taylor filamentary network. On top of which, the variation in polarization are large. We get maxima of around 45%, but we get also regions that are bright but totally unpolarized, which means that there are variation of a factor unity in the level of turbulence, or delta B over B, that we get through the system. Now, the crab was an interesting system, but I will move somewhere else to actually get some other result. The important things of the crab is that we were able to get the data for the pulsar. So these are the results that we got for the pulsar. Now, these results are presented in terms of Stokes parameter. I apologize. I know that it makes much more sense for theorists to think in terms of polarization angle and polarization degree. Unfortunately, when data have a low statistical significance, polarization angle and degree becomes highly correlated. So showing them separately, it's highly misleading. Stokes parameter had the advantage of being independent, and so they go their own way. So what you can clearly see here is that in X-ray, we got the only really significant measure of polarization at above 3 sigma, above 5 sigma, was at the very center, at the very core of the main peak, typically where all models predict it should be unpolarized. And we have also some evidence at 3 sigma of polarization on the wing of the main peak. And the polarization in the peak roughly trails on the values that we had in optical. I would say roughly because it doesn't really match well together. There is a kind of shift. It's hard to interpret where this shift comes from. Instead, the interpulse looks to be completely unpolarized, and if any, it's going, the polarization swing is going in the other direction. But one important result concerns actually the so-called bridge region, the region between the two peaks. Because we have upper limits on this region, but we can safely say at 3 sigma that the polarization cannot exceed 30%. Now, the bridge is an interesting region because essentially all the traditional inner magnetospheric model, polar cap, slot gap, to caustic, all the models that put emission, let's say, well within the light cylinder, all of them predict that the bridge should be highly polarized. Polarization of 60, 50, 80%. So all these models that predict a very high polarization in the bridge can very easily be ruled out. The only model that really survive, but it survived barely, I would say, are models that put the emission at the light cylinder or in the wing. So the one that essentially set the emission region in the striped wind or in the current sheet. But this barely survive in the sense that it's a last resort, I would say. And the reason is this. Okay, so this is a very simple model you can make of a force-free wind. You can take your so-called ballerina skirt structure for the current sheet. It performs quite well. This is an analytic model, but as you can see, compare even with MHD simulation, it does reproduce decently well the structure of the current sheet that we have in numerical simulation. Now, there is an ambiguity in using this model, and the ambiguity is tied to what do you assume for the velocity of the plasma. Force-free models do not give you the velocity of the plasma. Force-free model gives you the so-called drift speed, which is only one component of the velocity of the plasma. You have another component, the one parallel to the magnetic field, which is fully unconstrained. And so, essentially, you can pick the two extremes. You can either opt for choosing the drift speed as an indicative speed for your plasma, or you can choose to adopt a fully radial velocity, which was typically come out of MHD simulation. These two have a very different implication in terms of the properties of the light curve that they give you. Drift velocity produces light curves with two peaks of different brightness. Radial velocity produces light curves with two peaks with the same brightness. Drift velocity shows a weak dependence from the Lorentz factor. Radial velocity tends to give you very, very narrow peak because of caustic effect, and a very underluminous bridge. So there is something you can say about the light curves also from this. The point that I want to make, however, is that typically we benchmark our model for pulsar on light curves. Light curves are not as constraining as we would like them to be, for two reasons. First, it's a very, very easy to fit peak separation. That's just a geometric effect. twist and turn your pulsar, you will always find a way to having your peak separated by the route amount in phase. The other things that we typically fit is peak width. That also is not, in my opinion, very constraining, because by toying with the velocity and by toying with the size of the emission region, you can get the peak of different width by itself. The parameters that are really constraining, if you want to model pulsar light curves, are the intensity ratio of the peak and the skewness of the peak. How much a peak is broader on one side with respect to the other. Those carry more physical information. So if you take this simplified analytic model and you toy a little bit with the number, and you try to reproduce the X-ray data with the crab, that's what you can obtain. So the points are the X-ray measure, and the yellow and the blue curves which lie beneath are two models for the light curves of the crab. And you would claim that this model fits, I would claim that this model fits decently well the light curves of the Crab Nebula, by assuming that the emission is essentially confined in a very narrow region close to the light cylinder. It cannot be much more extended, otherwise you don't fit the peak brightness. But if you take this model and you compute the polarization, what you get is this, that it doesn't fit the data. See. So you get beautiful model for the light curves, but the magnetic field is not what you are observing. So these models is probably missing something, or probably missing a lot. I don't know exactly. But the point that I want to make is that polarization is far more constraining on the properties of the pulsar emission than the light curves. Of course, if you don't fit even the light curves, well, forget about it. But fitting the light curve is not enough, or having a decent qualitative model of the light curve is really not enough. If you assume that your emissions is somehow related to the geometric structure of your magnetosphere, then polarization will be a killer test of your model. So this is just to give you an idea. Now, the point that I'm showing here, as you see, have a very big error bar. We are requesting more times for the crab, so we hope to improve this error bar by at least a factor 2 in the forthcoming year if we get enough coverage of the systems. That depends on many things, including how long NASA will keep IXPE satellite flying. So we can go to other objects. One of the objects that I like a lot to talk about is Vela. Vela is being very strange for us because it was immediately clear that it was a highly polarized system. And by doing the space analysis, space resolved analysis, we were able to figure out spots in the system that had the polarization very close to the theoretical max. If you think that you are bound to have some depolarization just because of PSF mixing, that means that this system has probably an incredibly ordered magnetic field with an incredibly small level of turbulence, except that if you look at the spectral properties of Vela are no different from that of Crab. So if turbulence was your favorite way of getting a flat radio spectrum, that's not what's going on in this system, or you don't have that much turbulence in this system. The other aspect that's quite interesting in Vela, unlike any other PWN, is that the X-ray polarization structure matches almost exactly the radio one. Radio and X-ray particle are sampling exactly the same magnetic field. But if they both come from synchrotron and they're both sampling the same magnetic field and they're both have been accelerated somehow at the shock, you would expect them to have a more or less the same emission properties, not just the same angle. But if you look at the emissivity of these systems in radio and in X-ray, they are almost completely anti-correlated. This is the radio map of Vela. You can clearly see it's very bright on the sides. There's these two major lobes, and overlaid are the Chandra contour. But if I plot a Chandra image on top, this is what you would see. So it's very X-ray bright where there is no radio to find it, and it's very radio bright where there is absolutely no X-ray to find it. Now you can think, okay, fine, radio particle takes a longer time to cool, but remember, this is a system that is in the reverse, it is in so-called reverberation phase. This is a system that has been cleaned out of very, very old particles. So the radio particles that we are seeing here are not particles produced 11,000 years ago that have been stuck there forever. These are still young particles. They might have been produced, perhaps, if the X-ray one had been produced 50 years ago, the radio might have been produced 100 years ago. But still, you wouldn't expect that such a small difference in the injection age would cause such an enormous difference in the emissivity. And indeed, by words, you can probably fit and explain these, but if you try to do it numerically, you have to try to compute numerical model by setting shells and regions and advecting particles, it's almost impossible to get what you see, actually, once you take into account that radio are supposed to be all over, even in front of you and not just on one side. The other object that we've been observed, which is quite large, is MSH 1552. Now, this is a beautiful object, is well resolved. It fills essentially the entire field of view of the IXPE detector. What was nice in this object is we were able to measure the polarization in the jet. And we find that the polarization in the jet increased moving away from the pulsar. So there is a clear evidence that the base of the jet is far more turbulent than the tip of the jet. And probably these explain why these systems is jet dominated. The jet is much, much brighter than the torus in these systems, right? Because you have a more turbulence, which probably tells you that you have a more dissipation going on and more reconnection going on at the base of the system than what you have in the other object. Then once this turbulence is dissipated and it goes into the accelerating particle in some way, then what you're left with is the overall leftover magnetic field, which in the case of this jet is mostly an helical magnetic field. What is also interesting of this object, I cannot show it because the data have been submitted recently in another paper, is that the radio anti-correlate, for what concerns the jet, radio and X-ray are anti-correlated. Where you do see a very bright X-ray jet, there's absolutely no radio emission. And on those two, on the side of the jet, where you do see no X-ray, there are very bright radio features moving there. With the magnetic field, that doesn't really follow what we see in X-ray. So clearly there is an evidence that even here, radio and X-ray are doing something different. It's not really clear why or how. For these systems, we have even a tentative measure of the polarization of the pulsar. This is a particular pulsar. It's a pulsar characterized by one very broad peak, essentially. So we have only one measure, and that measure suggests it's compatible with the rotating vector model, so it's a standard way, but it suggests that probably emission is located at a high altitude. It's not one of these rotating vector models computed at the base, but you need to locate it almost halfway through the magnetosphere, your emission region, in order to produce what we observe. But again, the pulsar is not bright enough to get that much statistics, and this is an object that has been observed for about 1.5 megaseconds, so we are not going to get another 1.5 megaseconds just to push bias factor square root of 2 down the accuracy on this system. The last object I want to mention are Bauschock PWN. So Bauschock PWN are these systems that forms when the pulsar exit out of the supernova remnant and start interacting through the ISM. And traditionally, we see many of these objects being seen in H-alpha through the interaction with the ambient medium. And we also see the X-ray that comes from accelerated particle. Ultimately, originally detected in H-alpha, but the vast majority nowadays has been recognized by looking at the X-ray traits. Now, there is a subgroup of these systems that show these things, which are known as jet or features, or how you want to call it, but essentially there are X-ray particles where there should not be. These are particles that manage to emerge out of these systems and go in direction where they should not go, following the magnetic field of these, likely, but likely also enhancing the magnetic field of these. So the standard model for this object is that there are particles that escape from the PWN, moves into the ISM, but that's not enough. In order to see these features, you need also to amplify the magnetic field of the ISM and likely to amplify to very high values with the delta B over B of order 10, to give you an idea. Now, we had been able to measure one of these systems, but not one of the main one. And that measure came as a side measure out of the analysis that was done by IXPE of the Galactic Center. So in the Galactic Center, you have all these radio filaments, right? Whose origins is not really well known, but there is some idea that some of these radio filaments could be actually illuminated by pulsar. In particular, there is an object which is known as G0.13, where we see in X-ray. There is a trail of radio, it's like a radio curtain that follow it. It's not clear if they are correlated or not. there is a hot spot at the center of this filament seen in X-ray, which is supposed to trace the core of a PWN or possibly a pulsar. And these filaments is supposed to be something like the structure that we were seeing in the previous image. So we were able to get an integrated measure of the polarization of this object. Of course, it wasn't that easy. The galactic center observation has been a mess because it was a mosaic. There were lots of effects. There is lots of background. The signal is not very strong. I wouldn't bother you. But the point is that this measure suggests that this feature is highly polarized. And so what we are looking is X-ray synchrotron. And the magnetic field seems to be aligned with the direction of the feature. See, particle seems to flow along an overall magnetic field. Even if this high level of polarization is actually almost incompatible with the idea of a high level of turbulence in this system, unless the turbulence itself is highly anisotropic. So this was a tentative measures. We should have done actually probably last week or next week, something like that, the measure of the polarization properties of the lighthouse. So hopefully these will come out in the forthcoming month, and we will be finally able to understand if this feature is polarized or not, how much is polarized, and if the standard idea that we have on the formation of these features through self-amplification of the magnetic field by some form of resonant or non-resonant instability of particle that stream through is reasonable or not. If we measure a very low polarization, things will work. If we get a very high level of polarization, we will have to think about the physics of this system. And with this, I think I'm finished, and I will conclude here, leaving you with just the conclusion. Thank you.
Thank you. That was excellent. It's really very clear and wonderful introduction here. Thank you. Questions? Paolo, do you want to take over?
Sure. Or we can both. Any general questions about the talk in particular, and then we can open it up, about general questions about pulsars and polarization and things like that. Anybody there? Okay, I see Henrik. Okay.
Hey, beautiful talk.
Thanks.
Just wanted to ask, do we have some constraints of how fast this plasma moves away just from the new star brightness profile? The fact that it's that compact, can that be translated into some constraints on the velocity, or, you know?
So, okay, this is a big issue. So people have tried to make a model of the Crab Nebula by assuming a velocity profile that, so you advect the particle and you look how much is it. And in my opinion, none of these models work. So in the sense that you can always find a velocity profile that match, but this velocity profile typically you have to add some diffusion on top of it. So it's typically you have advection diffusion problems, and people have worked out with this kind of a beta profile for the structure. Now, if I look at my simulations, good or bad as they are, but the point is that there is lots of mixing in the nebula. So it's true that you would expect, roughly speaking, a shrinkage of the size, and this is what you would observe, but you do see X-ray very, very far away. I mean, if you have to go very deep. That's the only problem. If you are not deep enough, you will see the bright structure, but those are not bright because particles are there. Those are bright because they are Doppler boosted over you. So if you want really to see how far X-ray particles are, you will have to go deep down. So people have tried to model this. In general, these models work well if you put turbulence inside your system. Now, whether none of these models try to turn that turbulence into a polarized fraction. That's the only problems that we have. We haven't been thinking of doing that, actually.
Thanks.
Okay, another hand is Felix. Do you want to ask a question?
Yeah, thanks, Paolo. Hi, Niccolo.
Hi.
Question is about this last object in the galactic center. where is exactly located that? I mean, within the molecular zone or?
Okay, let me try to go back. Let's see if I can show you. I don't see my mouse. No, it's not really in the molecular zone. That's wait. Let me.
But how far is from galactic center? I mean, within 100, 200 parsec, 300 parsec.
I mean, okay, it's in projection, so we don't really know exactly how much is it,
Yeah.
but
Right.
yeah, it's something like that.
Well,
so
maybe I can explain why I'm asking this question. Because the radiation field in this area is typically very high, at least within 150 parsec is extremely high, something like 10 to 4 electron volt per cubic centimeter. And if it is the typical pulsar nebula, then magnetic field hardly could exceed much 10 microgauss, let's say, because just the power of the pulsar is not sufficient to bring so much magnetic field. Magnetic field could be much larger in this area, but it is the bubble, which is nothing remains from the original, right? So then we have a 10 microgauss and 10 to 4 electron volts. So it's about 1/2 order of magnitude more energy in radiation field. So if it's really synchrotron, so that implies 100 TV gamma rays, then that should be very bright TV gamma ray source. I mean, just explain logics. I mean, so radiation field is very high. And then is it true or not? At least in my memory, I don't remember TV possibly nebulae in that area.
I don't know if you can resolve these things because it's a very messy environment. So the point is this, okay? It's so all the objects.
How strong is X-rays?
Sorry.
Sorry, interrupted. How strong is X-ray flux? Is 10 minus 11, 10 minus 12?
I couldn't remember, but I will have to check the number. So the point is this: okay, the strength of the magnetic field in these features is kind of a tricky business because, for example, if you take the guitar, it has a very weak pulsar, which is of order 10 to the 32 Hz per second. But if you want to explain that features, you do need at least 40 microgauss. This is a system that is sitting in alpha, so it's moving in a system that's also partly ionized. So you see that it's not so obvious to put all of these things together. So in these systems in G0.3 we don't see the pulsar, so we don't know what is the strength of we don't know how strong it is, or what is its energetics. There is also the chance that you are not pumping the magnetic field with the pulsar because you have plenty of these filaments, right, in the galactic center. We don't know what is their origin. There might be local enhancement due to turbulence in the magnetic field that cause layers piling up, and you will just be illuminating them. So it's not obvious that the magnetic field should be very low. So in the guitar, the estimates is about 40 microgauss for a system that's quite.
Oh, that's interesting.
No, you simply.
It looks like very strong here.
Exactly, it's a very strong claim. If you the point is that if you take particle at the pulsar voltage, if the magnetic field is smaller than 40 microgauss, you don't see X-ray. That's the argument. So it's really either is that or we haven't understood anything about particle accelerated, probably. So it's tricky. But the point is this: I agree with you. So the polarization is a strong signature of what we are looking at.
So it's no doubt it's synchrotron, and if you don't have gamma rays, most likely you don't have strong gamma rays. It is magnetic field should be very large, kind of 100 microgauss.
Yeah.
That could not be powered by pulsar.
It's hard. It depends. It depends on the extent. I mean, I agree with you. 100 microgauss is a lot. So it sets a very strong constraint. These systems are really tough to make.
Okay,
Yeah.
thank you. I got.
Yeah, Felix, one question. So the radiation field is high, but I thought in galactic center, like the magnetic field is much higher also. If you just
No, Paolo, if magnetic field does matter, what is magnetic field in the galactic center if you are talking about the pulsar nebulae? Because you don't have anything from relic from, from galactic center. You push this out and don't bring magnetic field from the pulsar. And if pulsar is more strong, then it should be 10 microgauss. So nothing to do with the magnetic field in yes, you are right, it's strong. But if it's pulsar in nebulae, then you clean up this area and bring your own magnetic field from the pulsar.
Yeah, but if we have particles escaping and then they compete with Compton, so they shouldn't be a gamma ray source, maybe.
Yeah. Well, so it's a very interesting point because synchrotron, there's no doubt after polarization that is synchrotron, no doubt.
Yeah.
And then we could calculate what should be magnetic field if we know radiation field.
So
and
this is
very strong.
Let me make one point. This is not the magnetic field of the pulsar wind.
Yeah.
Cannot be the magnetic field of the pulsar wind.
Yes.
So if you want to make that strong magnetic field, you have to make it through amplification. Resonant or non-resonant, I don't, because you have particles that escape. Particles that escape can amplify magnetic field through resonant or non-resonant instability. So the general idea that we have in this object, but it's an idea, is that you have a flow of particles, leptons, that can be charge separated or can be charge neutral. That's not clear, depend on many things on how the particle escape. But if you have let's say a charge separated outflow and the net current, you could potentially drive some streaming instability that amplifies the magnetic field. Now, how much it gets amplified, does it get amplified to the values that you need, and how does that feed back on the current of the flow of the particle, that is something that we are trying to investigate, but as you can see, it's not something that you can do. This is the nonlinear phase of an amplification, an amplifying instability. It's typically we have to do with numerical simulation.
Yeah. Thank you. Thanks.
And Rashmi's had her hand up for a while. Okay, thanks a lot for the answer.
I have a quick question about the so you talked about the IXPE. You now have basically spatial resolved maps now of these with these IXPE, which is pretty amazing. And then you showed the map for crab. Could you mind going to that?
Yeah.
Where the intensity does not line up with the axis as you.
Okay,
is this something
the polarized fraction does not align with the axis at all.
that is? Is there an easy way to understand that? And do you see that in other?
Okay. No, we don't see. So the point is that in the other systems, we see a very large level of symmetry. In Vela, it's decently symmetric. And in MSH 1552, it's also decently symmetric. At least the level of asymmetry that we have in polarization is not much different than the asymmetry we have in emission, which might tell you that some region might be more compressed or less compressed. But in the crab, the level in polarized fraction that we see, it's basically much larger than the small variation in luminosity of the torus. The torus is slightly brighter on one side. What we have noticed, however, is that there seems to be a correlation with the spectral index. So the region where the polarization is higher seems to be harder than the region where the polarization is smaller. Now, what does that mean? I have no idea. The other point, which is strange of the crab, is that naively, what we would expect is that, okay, you have this beautifully ordered magnetic field, this loop that comes from the pulsar. Pulsar wind is beautifully ordered. You get this pulsar wind, it's impact with the shock. So you would expect your downstream of the shock to have a very ordered magnetic field that eventually get mixed up in the nebula. The nebula, you have Rayleigh Taylor finger, you have matter that flow at different speed. So the naive expectation at the beginning was that the central region would have been much more polarized than the outer one. But now I'm not superimposing here the images, but you see the intensity is shown in the picture of the left. You can clearly see that it is not the brightest part of the torus that's highly polarized. It's the edge, the outer edge of the torus that's more polarized. Now, why a region there should be more polarized than the inner region is not clear. And this image have been taken care of the pulsar. So a pulsar has been subtracted. You can redo the same analysis just by taking the off pulse. We now have enough counts. This was a preliminary, this was the first observation, but now we have accumulated about, I would say, 400 kiloseconds of observation. So actually we are saturating the systems. The crab is an awful object. It has telemetry problems, so we cannot observe it too long, otherwise we saturate the buffer. And it's clear that that what we found in the first simulation, it's there. The center of the systems and the bright part of the torus are unpolarized. Or not unpolarized. They have a very low level of polarization, let's say. Polarization increases as you move outward, which seems to suggest that the inner region of the system is more turbulent, and turbulent gets somehow dissipated and then stops working at the edge. Now, if I had to put forward a suggestion, my suggestion would be that perhaps the Rayleigh-Taylor finger that we see in the Crab Nebula that penetrates about halfway through the PWN might end up stabilizing the magnetic field. These are high mass finger that protrudes inward, and then maybe once the magnetic field starts flowing through this finger, it gets stabilized by then, which is not what you would expect. You would expect instability to make things worse, but globally speaking, it seems that magnetic field gets relaxed to a more. But why it looks so different in the northern than in the eastern side, and is so asymmetric, that's absolutely not clear. We don't, there is no other things in the nebula that is indicative of such large variation. There is no structure, no thermal filaments, no radio filaments that pinpoint to anything special going on one side with respect to the other.
Thank you.
Maybe I'd ask a quick. So what you just said about the asymmetry, does that indicate that it's not such a clean system? And if you have fingers coming in, there's some external medium that's causing responsible for this, and can explain maybe the difference between other ones. Like when you have the recollimation to make the jet, is that purely in isolation and just the flow hitting and coming back on itself? Or can the external medium, somehow external boundary conditions influence that?
It could, I agree with you. I mean, probably the crab is not that clean system. It's true. And I would say that the villa looks far more cleaner than the crab.
Aha.
Notwithstanding the fact that the villa is a nebula that's going through the supernova remnant. So you would expect it not to be that clean. But apparently, if while you look at X-ray, you look at the internal region, villa appears to be a much cleaner system than the crab. So it's probably something that has to do with the dynamics. I mean, I cannot really, we don't have a good model for that. And the problem that why we don't have a good model is that once you start to, 3D model cannot resolve the instability at the boundary of the system.
Yeah.
That's the worst thing. So if I had to run a three-dimensional model with enough resolution to resolve the Rayleigh-Taylor instability that's going on at the boundary, I would need, just to be honest with you, a 10,000 cube simulation. That's out of the business today.
Yeah.
More, I don't know.
Wow. Yeah, because we've been playing with 2D versus 3D jet simulations. They're completely different, like the instabilities.
You tell me. So that's why I say that probably we need to be clever in the way we include small scale stuff into larger scale. We cannot resolve into larger scale one.
Okay, thanks. And we have another question from Haifeng.
Yes, I just have a very small question because you have mentioned so much knowledge about the magnetic field and magnetodynamics, turbulence, and so on. How do you consider the gravity, the basic force in the nature when you do this topic about the pulsar wind and nebula?
So okay, so in terms of gravity, it's not very, I mean, the pulsar is not very relevant per se. What we have is actually that it might be important in so the related Taylor instability that we see at the edge of these systems is mostly due to the fact that the PWN are having accelerated expansion. So locally, the interface it's highly unstable because they find in a local acceleration. Now the acceleration in PWN is strongly time dependent. It's very strong at the beginning. In the first few hundred years, it's incredibly strong. And as the systems evolves, it gets slower and slower. So to a certain sense, you might expect that there is, if this Rayleigh-Taylor instability, it's what, let's say, dominates the polarization properties of these systems and what makes these systems either more massive or less messy. And if this is associated with the how fast the systems accelerates, then probably you would expect systems like the crab, which are younger, to have a magnetic field which is more patchy, let's say, which is what it fits. In systems that are older, like Vila, to have perhaps something more clean. But that's mostly speculating. In reality, in terms of roles, I mean, the gravity is not that important. So even for the pulsar magnetosphere, we typically, for the region of the magnetosphere, we care about the right cylinder. It's not very relevant.
See, yeah, thank you.
Any more questions? If no one else has had a question about the variability, you showed us variability in the simulation, but what's driving the variability?
It's vorticity. It's basically it's I don't know how many of you know this. There is this called standing shock instability. And let me try to go to an image. I'm trying to I cannot move the mouse, but I might be able to show you. Okay. So what happened is this: you have this shock which is oblique, so is oblate, and so you drive a vorticity downstream of the shock. Now vorticity is very strong here, so you have essentially the downstream velocity is a fraction of the speed of sound. So you get lots of vorticity. This vorticity drives sound waves, and the sound waves propagate backward along the shock because you are in a subsonic system. And so they propagate backward and they corrugate the shock. So ultimately, is this a feedback from the fact that if you corrugate the shock, you produce vorticity. The vorticity produces sound waves propagate backward because you are in the subsonic system. They surf the shock, they corrugate it, and the systems repeat, rinse and repeat, essentially. So it's something that has been seen inside out in simulation of supernova remnant. Is essential. Is a self-driving instability, if you want. And this is the pure hydro instability. There's nothing to do with the magnetic field. So as long as the shock is oblique, you will get this kind of instability. You will get this kind of variability. And the issue is that, as I saw you, given that this vorticity happened with a very strong speed, it gets to 0.2 or 0.3 the speed of light, and given that all these rings are due to Doppler boosting, so to the values of the velocity that points toward you, changing the amount of the line of sight component of the velocity by plus or minus 0.2 pushes the luminosity up and down by factor unit.
Yeah. Wow. And does the time scale work out? Because if it's sound waves, there's some
no, the time scale works out. So there are two things that works out very well. The time scale works out. So the time scale, you get the right time scale compared with what we see in the nebula. And you also get the right direction of the waves. So in the nebula, you see these waves that tend to propagate outward. And if I take the simulation, I do see these waves moving outward. It's just the amplitude of the wave that gets wrong. But if you want, speed and periods are the right one, which, again.
Yeah, it's great. Okay. And Any other questions or? One other thing, you mentioned like turbulence, strong turbulence, and corrugated shocks. People have been doing sort of PIC simulations of this kind of thing, and you find that the acceleration works because the shock is no longer this nice structure. So even if you loop immediately get it vectored out, you hit some other part of the shock, or the turbulence can mess up the field.
Yeah, this relativistic shock is a tricky business.
Yeah.
Because there you have a Lorentz factor. So it's true in non-relativistic shocks, corrugation might help a lot. In relativistic, I'm not so sure because once you factor in the Lorentz factor and the fact that downstream you still have a very high speed, it's a bit tricky. It might work, I mean, but it's very problematic even to do simulations of strongly corrugated shock in a relativistic system just because of the skills you're going to compress.
Yeah, but I guess people have tried this, and Martin Lewan has put in artificially turbulence, and if you make it strong enough, it wipes out the field. So things can diffuse around and get back eventually, and it kind of takes off. But the spectrum is still too steep, I guess you're saying, for the radio.
With the radio, you cannot. So if you think of something bouncing back and forth through the shock, you get 2.2, 2.3, depending. It's definitely too steep for the radio. It's in some PWN is 1.1. So
yeah. Okay. I'm talking too much, Brian. Maybe you have some opinion about this, or
Yes, I have some strong opinions on this.
Awesome.
So I mean, I think this is a misconception about relativistic shocks as well in general. I mean, once you introduce various drifts, you can actually get very, very hard spectra, and returning to the shock is not a problem at all. I mean, this has been shown now at least in a number of Monte Carlo simulations, and there's also some preliminary particle cell simulations by Benoit Cerruti and Gwenel Gisanti. So I think it's still, I agree, Niccolo, that there's a lot of problems, but and it's early days, but there's still definitely avenues, and I think nature seems to find a way to do these things. So you can get very, very hard spectra from shock acceleration, and the issue of the downstream moving fast is not really that much of an issue.
No, it's true. But remember that in PWN there is one major problem is that you need a mechanism that produce you two different spectra, one in radio and one in optical X-ray, because you cannot map the entire spectrum with just one slope. And this we know almost for sure because all the models that we have require an injection with the broken power. And one of the biggest issue with the many models is how do you ensure that you get a broken power? Because if you assume, one of the biggest issues, if you take a different acceleration in different position of the shock, then you might get radio and X-ray which are differently, but then why don't you get a jump somewhere? So how do you get something that has a break and not a jump between optical and radio? And the ugly point is that this is seen not just in the crab, which is fine. You get something similar also in Bauschock PWN. And Bauschock PWN are systems where really you don't have much time to accelerate particles because particles flow away in the tail. So it's so you have to accelerate beautiful non-thermal spectra, and if you look carefully, the acceleration time scale is the light crossing time of the system. And that makes things quite demanding. And if you look at their spectra, they are no different than normal PWN. So it's as I say, I'm not making claim that our acceleration model don't work in general. They can be tricky, but they tell us, I mean, they have a lot of implication in terms of the underlying model for how the pulsar works and how the plasma behaves. And we will have to take all those implications into consideration because it's not just fitting a spectrum. You want to put everything together at the end of the day.
I agree, but I think, like I said, there's still ways to do this within a shock acceleration scenario, but for another day. Thanks, Niccolo.
Yeah. Okay, Felix, you got another question? Yeah.
Yeah, just in this context, I was not going to ask question, but some independent of the mechanism of acceleration. We need a very large magnetization to get the very high energies. Like maximum energy depends on magnetization parameter. So what your simulations show or predict, what could be the maximum one?
So in my simulations, I mean, how to say, typically at the shock, I don't get above, in the crab, I'm doing the crab simulation have been done for that system, 300 for the crab. I'm talking about the crab because we have done simulation having the crab in mind. So all the parameters are kind of set for the crab. In our simulation, the magnetic field at the termination shock does not go above, I would say, 300 microgauss.
And that is 0.1, right? Approximately.
This is yes. This is okay. No. There are 2 points. Okay. Yes, this is sigma 0.1. You're right. But in our simulation, we always assume a striped wind. If you don't take, so when you look at what sigma is, you have to understand if sigma you have to the sigma that you have before the stripes are dissipated or after the stripes are dissipated. So our model have a pre-dissipation sigma of 1. So there is as much energy in the magnetic field as there is in the plasma, except that when these stripes hit the termination shock, they all get dissipated. And the effective magnetization is about 0.1. But if you start with the wind, with the magnetization, with the wind that is 0.1 magnetized and striped, then you will get an effective magnetization which is 10 to the minus 2. So you have to take into account this complication of our simulation.
But never close to 1.
The effective is never, but the wind magnetization is essentially 1.
Mm-hmm.
And the point is that in this in the simulation I cannot do the reconnection of the current sheet. So I put it by hand by dissipating part of the magnetic field by hand. That's the only things I can do. So the pre and post, there's a factor 10 difference.
Okay. Thanks.
So we typically when we quote sigma, just to give you an idea, when in the paper we quote sigma, we always mean the sigma before dissipation. The effective sigma in the bulk of the nebula, we never state, and we let people compute it by hand.
But the scalar coronity calculus gives that.
And the coronity gives 10 to the minus 3, but if I use 10 to the minus 3, I don't get the jet.
Mm.
So if you want to get the jet in the nebula, you need at least 10 to the minus 2. That's the minimum to get a very weak jet. You have to go 10 to the minus 2 or above.
Mm. Okay, thanks.
Yeah, I think, Felix, we should end here.
People are going, yeah.
Paolo, you should ask Paolo. I am guilty. I was so late.
No, that's okay.
I'm moving, always moving from place to place and mixing the time difference.
Yes.
I'm sorry.
Well, I'm glad you could join. But that was a really excellent talk and great summary, and very, very much enjoyed it. Please send us the PDF. Send me the PDF, and we will post it.
Yeah.
And
Thanks, Niccolo. Yeah, lots of stuff. It's good.
You can continue to join.
Thank you.
Please continue to join these seminars.
Sure.
Participate.
So just a stupid question, but should I send you an email for joining the mailing list? How does it work?
Well, I have added you. You should have. Did you receive an invitation? You must have received the announcement already, right?
Yeah. I got received the announcement. I wasn't clear to me if it was just for mine or.
No, it was. We've added you to the mailing list, but please continue to join. It'd be great to have you participate. Okay. I think that's it. Thank you very much. Brian had a question for you, Felix. Where are you now?
I'm in Armenia now, Yerevan.
Armenia. Wow.
All right. It's good to see everyone and hope to see you again in 2 weeks. Bye.
Bye.
All right. Thanks again.
Thanks, Paul.
Bye.